Hi. Okay. Okay.
Ready to go, you think?
I will see. I have to.
All right. So it looks like we've reached the very last lecture. I just have to say before we get to Mirjam's lecture, these are the best shirts. I'm going to wear this with pride. I have a snail riding the watermelon and vomiting out the moon. I mean, this is pretty much the best I've seen. So nice job. So for the very last lecture, we're happy to have your scientific organizer, Mirjam Cvetic, telling us about gauge symmetries and F-theory.
Well, thank you for this invitation. Actually, introduction, since I probably scheduled myself. Yeah, exactly. And basically, what I try to do is save the best for last. We'll see if that's really the case. I think it was very intense past 2 weeks for me as well, and 4 weeks for all of you. So I hope the experience was a great one for all of you, and this lecture hopefully will also wrap up some of the things that we have heard about most of this week, in particular in Timo's beautiful lectures. He very carefully and pedagogically derived aspects of geometry of F-theory compactification by studying geometry of elliptic vibrations on Calabi-Yau m+1 folds, and in particular what he carefully outlined is the origin of non-abelian gate symmetries as appearing in codimension 1 singularity is of elliptic vibration, the matter, localized matter that appeared at codimension 2 singularities of elliptic vibration, and also the whole procedure how to determine in codimension 1 the representation of non-abelian gauge bosons, so namely the non-abelian gate symmetry, and as well as representation of matter in this context. To describe chiral matter in this context in 4 dimensions, one had to turn to the concept of turning on 3-forum potential via M-theory duality, namely 4-forum field strength flux that when integrated over matter surfaces had non-zero value, and that in the, I believe that was your 4th lecture, 5th lecture, that determined the type of that flux then determined the chirality of chiral matter, so namely number of chiral superfields. And then also as the last important ideas also had to do with making this compactification consistent when we turn on the G4 flux, which led basically in M-theory version to tadpoles, and analogous formulation then for F-theory languages that turning on G4 fluxes induces the D3 tadpole. So basically in these constructions we have to turn on also not only the what we refer to as PQ7 branes, but as also the appearance of localized D3 branes in the internal space. So the techniques were rather, well, what can I say? They were pretty intense and non-trivial aspects of both differential and algebraic geometry, and the main ties between geometry that we find in these singular elliptic vibrations was tied to physics via M-theory duality. And so all these aspects, in particular about the features of non-abelian gate symmetries and matter representation, was carefully worked out in Timo's beautiful lectures. So the topic that I want to address is addressing not non-abelian gate symmetries, since this you should know all about now, but the features of pure abelian gate symmetries in F-theory compactification. So in particular, appearance of abelian gate symmetries which would be associated with a product of abelian U1 gauge factors. Let me denote them as a number of factors to be n minus 1. Okay. And also the appearance of discrete, really abelian, discrete gauge symmetries which in this context would be related to the discrete symmetry Zn. Now, while in principle one can formulate these geometric ideas for the origin both of abelian gauge symmetries and discrete gauge symmetries for any factor n, I will primarily focus on the case n equal 2. That means appearance of an extra abelian gauge symmetry and appearance of Z2 discrete symmetry. The generalizations as well as references are in the additional PDF notes that are posted on wiki page. Okay. And I think it's a useful, more sort of an overview of the topics that I'm going to discuss here in more concrete context for the special case of just n equal 1. So what I'll try to convey to you is that actually the origin, geometric origin of those type of symmetries is different from the ones of non-abelian gauge symmetries. It's associated with new type of geometry of fibrations. Of torus vibrations. Okay. And in particular, what we will see is that the appearance of abelian gauge symmetries will be associated with appearance addition of, so the case 1 will be associated with the appearance of additional sections in elliptic vibration. Okay. So in addition to zero section that Timo clearly emphasized in terms of Weierstrass parametrization of the elliptic vibration, that would correspond to n equal 1, just one section. Now we will have one additional section. So altogether we would have n sections for U1 n minus 1 gauge symmetry. So we are dealing with the zero section, but now in principle we could have additional sections. Altogether n sections that leads now to U1 n minus 1 in F-theory language. Okay. Furthermore, for the abelian discrete gauge symmetries, a new phenomenon will happen. The description of F-theory, where we have non-abelian discrete, I'm thinking about non-abelian discrete symmetries all the time. So, but here we are dealing only with abelian discrete symmetries. Will be associated with new type of vibration, which will be vibration only of torus itself without sections. Vibration on genus one curve, okay, with no sections, but this geometry will have what we call multi-sections. Sections, basically square and square of section, the notion of that type. So multi-sections, so with n section, this would be describing the geometry of F-theory compactification, where the gauge symmetry is Zn. So in addition, actually, in addition to tools that Timo presented in studying geometry and then, as a consequence, physics of F-theory compactifications, which were basically algebraic geometry and or differential geometry techniques. Here we observe another intriguing connection to mathematics, namely the ties to what we call number theory, and in particular the sections associated with the elliptic vibration form generators of a new type of group named under addition of those sections, and it's referred to as number theory Mordell A group. In this case of rank n-1, and is associated with additions, a group of additions on this of sections associated with the elliptic vibrations. The geometry that signifies for us the appearance of discrete gate symmetries, namely vibrations with only multi-sections, are also tied to another number theory group. This would correspond to these geometries organize themselves in a specific way and are associated with the appearance of what we call Tate, Shafarevich, a group in this case would be the group Zn. I'll briefly mention possibly that, but it's sort of intriguing also from the math perspective that to describe these aspects in this geometrical phase of theory, string theory, we are encountering new type of intriguing features, both from the math perspective and I hope to draw also physics consequences. Anyway, let me remind you what we have seen in Timo's lectures before I continue. Well, let me not do that yet. Okay, so those are just some basic motivations and advertising the key geometric features in describing this type of gauge symmetries in F-theory. But let me just here I prepare sort of the outline that I'm hoping to cover. So as I said, I'll focus primarily on the case that corresponds to only one gauge, U1 gauge symmetry. This will be associated just with one additional section, and the corresponding Mordell V group will be of rank 1. I will argue also about features of the matter that is now charged under the appearance of matter geometrically that is charged under this U1 gauge symmetry, and features of the possible charges that we get in this context. And if I have time, right, maybe probably just in words I'll mention an intriguing idea that actually as we move in the space of moduli where we have elliptic vibration with one extra section, the additional section could collide with original section. At this point, we have only one section left, so we have no U1 gauge symmetry, but a new phenomenon happened. This U1 gauge symmetry turns into non-abelian gauge symmetry. So it's an intriguing geometric process that happens in this context. And in field theory, we refer to that as unhixing phenomenon. Namely, in the field theory, breaking SU2 down to U1 is due to giving vacuum expectation value to some matter field in the theory. Now, if this expectation value of this field, vacuum expectation goes to 0, we recover back SU2, and then that means we unfix this. Anyway, then in the second step, I will actually now turn to Z2 gate symmetries again, really pointing out how to connect geometry with an additional section to a geometry where there is no section anymore, but the two sections are glued into bisection, which then results in describing F theory on with gate symmetry Z2. So both geometrically, I'll try to argue about this phenomenon, and then in field theory, we will also see how this is realized by having now matter with the right charge in the original construction, that when this matter gets vacuum expectation value, indeed it breaks in the field, at the field theory level, the theory to the discrete Z2 symmetry. And maybe if I have some time, probably not, mention some connection of this bisection geometry to Z2 Tate-Farevich group. Again, no details about that, but all this involved techniques that both Timo developed and I would like to highlight here really had a goal of applying these ideas of F theory to construct globally consistent models for particle physics. In particular, there was a tremendous effort in constructing grand unified models, but maybe, of course, because that's closer to my heart, in the notes I have provided, there is example where all these techniques are basically effectively applied for global construction of a model that would have standard model gauge group, which has an additional U1 gate symmetry and is supersymmetric, as well as with all this turning on G4 flags, ensure that the chiral matter is represented by 3 copies of quarks and lepton families. And maybe 1 or 2 words about the future outlook. Again, the case is very, I'm going to take only n equal 2 case, but for the things, as I already advertised, look up in supplementary material, and in particular, for each of these generalizations, they are the right relevant references, because these ideas happen to be very dynamic and intense field of research in the past 5 years or so. Okay? All right. So now, in order to motivate a different nature of U1 gate symmetry relative to non-abelian gate symmetry, let me just remind you that, but I shouldn't take too much time, that appearance of non-abelian gate symmetry, right? Symmetry was based on constructing singular elliptically fiber Calabi-Yau m+1 fold that was elliptically fibered, namely that was the elliptic curve fibered over n-dimensional scalar base. And this vibration was specifically represented by Weierstrass normal form, which I'm going to write a number of times, even in the context of the study of abelian gate symmetry. Okay. So the non-abelian gate symmetry, if we are dealing with the base, complex base of dimension n, it could dimension 1 locus. So let me just define this as a discriminant of elliptic vibration vanishing at codimension 1 locus. We obtain the fiber. The vibration can degenerate along this locus. So the previous torus that we had now degenerates. And the nature of the singularity actually quantifies for us at the end what kind of non-abelian gate symmetry we have. So what Timo was doing, he went to resolve Calabi-Yau n+1 fold, so in the resolution. This degenerate fiber, this degenerate fibration over codimension 1 locus was actually resolved, made non-singular. So in the fiber, along this codimension 1 locus, what you've seen is that this degenerate torus was now built out of a set of P1s and also the affine one that intersects with the 0 section. So that was a 0 section always because it was Bayer stress. So there was another P1 associated with affine node of the Dinkin diagram. So that is P01. And so there was sort of a particular web of this P1s, and so this resolution in fiber resolution is a bunch of these P1s, and what I'm sort of drawing is what we call in this case IN fiber, okay, and is then this IN fiber was in 1-to-1 correspondence on this side with the nature of the singularity at this codimension 1, which we parameterize by the discriminant, and order of vanishing of the discriminant, and this F and G, which were specific sections of the line bundle of degree 4 and 6 of the vibration. So degree of 0. So order. So that was the order N00, I think, that produces for specific case of IN fiber, whose resolution is of that form. Now we have a resolved vibration, and this Dinkin diagram actually is associated with the appearance of SUN gate symmetry in this case. So what specifically happened is each of these P1s fibered over this locus 1 defines what we call resolution divisor. So we had resolution divisors, which was described as this P1, PI vibration, okay, and then let me call that PII vibration. So that's defines a resolution divisor over locus in codimension 1 in the base. Okay, and to determine basically the origin of the non-abelian gate symmetry, one has basically done now the intersection of this resolution divisors classes with the P1s. So this with the P1s. So let's say with the Jade P1, and let me stay with the same I, and that basically these intersections were parameterized by the Cartan matrix. So that was Cartan matrix. In this case is precisely Cartan matrix of SUN gate symmetry when we have the set of resolved this P1s that resolve the degenerate fiber, and so this is Cartan matrix. Okay, and further using Poincaré duality, the resolution divisor is dual Poincaré dual to 1,1 forums, and those were those 1,1 forums that Timo used in the reduction in M theory language of C3 on this Calabi-Yau n plus 1 fold and obtain a I gauge bosons in 4 dimensions or 6 dimensions, whether we took n equal 2 or 3, and those were now gauge bosons associated with Cartan generators, gauge bosons associated with Cartan generators, Cartans, in this particular case, the rank of SUN is n minus 1, so Cartans of SUN. Anyway, let me not dwell on this. I just want to remind you that actually this is completely different phenomenon. The divisors that support the new non-abelian gauge bosons associated with the Cartan generators are the divisors associated with singular vibration in codimension 1 in the locus. And these divisors, in the result picture, these resolution divisors, one often refers to as vertical divisors. They are associated with some codimension 1 locus in the base, and that's the whatever fiber does. In any case, the matter also appears in this context, and the matter appears in this context in codimension 2. So typically, again, so matter here appeared. We have codimension 1 locus. Either it intersects or there is another codimension 1 locus, and that at this intersection, this is now codimension 2 locus, codimension 2 locus. Okay, the fiber also degenerates. Okay, so the thing's degenerate here. So we have codimension 2 singularity. And once we go to the resolution, so as we go to resolution, what happens typically is that this resolved fiber, actually that is, in the simplest case, would be of this Kodaira type, actually typically gets new splits. So, for example, if we have now this is, okay, P0, and then there's always the 0 section here. Anyway, P0, 1, and so we have this this P1, 1 to Pn minus 1 divisors in the resolution at codimension 1. Now when we do the resolution, what happens at this codimension 2, typically some of these fibers split further. Those were the split curves. So instead of having now this P1 that goes along, specifies one resolution divisor in the Cartan, associated with the Cartan generators. Now this becomes typically a split fiber, P, say, I'm just looking at one of them, plus, okay, and P minus. So splits into two P1s, so P1 plus or P1 minus in this case, and actually it also, they touch, they typically touch into points, and so one often writes this resolved when this P1 splits into two as P1 plus, there is a often picture like this in the resolution of having now this single P1 becoming two P1s, and that is typically now the I2 fiber. Okay, so the split of this P1s now at the codimension 2 signifies for us the new features of the representation of the matter, and Timo carefully worked this out. Namely, what one in this context technically does, calculates the intersection of the resolution divisor, say, okay, with the one of those P plus or P minus. So let me do it like this. Okay, and calculates. This would give you a particular number. For example, if for this one it was 2, in this case that he showed that was typically 1. So some number. I don't want to go into technical details because Timo really spent lots of time on that. So in any case, this intersection signifies for me now the actual one component of a non-abelian representation of the matter under this non-abelian gate symmetry. So, and then you work it out for all these other things, and you get the full-fledged representation that in this case, for example, signified the fundamental representation of SUN. Okay? So that was just reminding you, and I'm spending too much time because now I'm, 1/3 through my lectures. But I wanted to tell you that because I want to now contrast the appearance of abelian gate symmetries with this picture that is so deeply connected to this resolution divisors associated with CUDA measure 1 singular in the base, and we often refer to them as vertical divisors. Okay? And now let's go to the new features when we are dealing with abelian gate symmetry. A number of times I already announced that, and I want to claim that. Now let's go to abelian case. So when we have U1, appearance of U1 is in 1-to-1 correspondence of additional section on elliptic vibration. Okay. And by the way, these aspects were all bits and the core things were already in the original papers by Morrison and Vafa in '96, and then it was forgotten, and then it was resurrected about, I would say, 5 or so years ago, or maybe a little longer, also with Timo's earlier efforts. So let's get to that. So what I want to show you, if I have now geometry where elliptic vibration has one additional section, this will produce for me a new divisor, okay, that will support 1,1 form that will produce via M-theory language a new gauge boson, but only 1,1 form and only one gauge boson, and this gauge boson would be U1 gauge boson. Okay, so so what I'm saying is we are having, as I said, in the Weierstrass parametrization, as Timo clearly explained, right? We are having elliptic vibration where we have a mark point, okay, on a torus that becomes a section when fibered over the base. So this mark point I'm going to call as 0. I think you call it as 0, right? And then it's in the vibration as we go. This is then, and then as I keep moving right over the base, that becomes section. All right. So the way we represented this 0 section is in the Weierstrass parametrization. So namely, writing the elliptic vibration as hyperplane constrained in x, y, z being coordinates of weighted projective space, 2, 3, 1. So those are the coordinates of the weighted projective space. When fibered over, F and G have to be the sections of a line bundle of degree 4 and 6, and altogether also x, y, and z become sections, namely certain polynomial functions of the base coordinates. Oh yeah, thank you, of course. Thank you. Anyway, so So already the zero section was actually a solution of this hyperplane constraint that corresponds to x, y, and z equal to 0. And then we use the scaling symmetry of this weighted projective space that allowed us to fix the x and y to be 1, 1. So this was then the promoted as a zero section over associated with this base coordinates. By the way, let me just, for simplicity, I'm going to focus on n equal 2 case. So B is 4-dimensional. Two complex dimensional. Anyway, so what I'm saying is I want to adjust this f and g polynomials in such a way to have another rational section solution. So I can, in principle, by adjusting f and g, find another solution for a new section, rational section, which I'm going to call x1, y1, z1, which will be solution of this hyperplane equation, okay, where, of course, everything defined in the field of the coordinates of the base. So if we have, in the presence of this specially, adjusted values of f and g's, if we get a new solution, this would now, in principle, generate a new section. So let's say we have a new, at each fiber, we have a new rational point. And then as we fiber over, this is associated with the appearance of a new section. Okay. It was, in general, the appearance of each section, okay, allows us to define the divisors in a canonical way. Even zero section by itself. So if I have a section, so if I have a section as 0, this allows us to define the corresponding divisor as 0, which is a 4 cycle in this Calabi-Yau space. So it belongs to 4th homology in the space. Okay. And basically what it is you see when I move, okay, so this oh sorry, this was not this, I should have, this was just at the specific fiber, but now we move, right, and then the sections S1, the sections then define precise meromorphic map from the base to this rational points at each fiber itself. So so having a section as 0, as we move there, basically we have unique map from all these coordinates of the base, okay, with the unique map to the locations of the rational points in each fiber via the section condition. So so for S0, basically the class of these divisors, which are 4 cycles in this whole space, is basically homologous to the base, in this case B2. Now if I have a section S1, another rational section, I have another map of all these coordinates, okay, onto rational sections at every point in the fiber. And so that would, in principle, for S1, so this would be somehow be associated with S0. Divisor. This, yeah, and then in addition we would have now the divisor that is sort of a distorted copy of B2 that is associated with section S1. Okay, so let me draw this divisor now. Oops, where do I have this? Anyway, so I can. Yes. It would mean that it will be really some specified, really in terms of holomorphic polynomials of the base coordinates. Yeah, that's basically because, you know, in this vibration, those are sections of certain line bundle, right, which are holomorphic polynomials. And then if I have a relationship, right, that would specify a section, then these guys would be completely specified by some rational polynomials of the base coordinates. Yeah, I'll show you an example of that type, okay, concretely. But you need some specialization of F and G. Okay, anyway, let me say, what I want to argue is that in addition to the divisor associated with the zero section, there is now a divisor associated with the additional rational section. And it's a divisor, right? It's a 4-cycle sitting somewhere in this Calabi-Yau space, okay, that is effectively some kind of copy of the base. Okay, so there is a natural divisor that comes with appearance of S additional section, and I'm going to refer to this divisor as S1. And of course, it also sits in the, it's a 4-cycle in the whole space. Okay. Now, this divisor is completely non-singular, right? Unlike those vertical divisors that were still singular and we had to resolve them, okay? They sort of sit somewhere in this space, and they are there. There's nothing I mean, they are part of this fourth homology group of this Calabi-Yau, in this case, threefold. Okay. Actually, this homology group in math community is also referred to as NS. So this is Neron. Right. So this is referred to as Neron-Severi group. Severi group. And actually proving that such divisors really exist, you know, in such elliptic vibrations with additional sections is due to the theorem of Shielda, Tate, and Vazir. Okay, due to Shielda, Tate, and Vazir. Okay, all right. So in principle, you know, having such a divisor, horizontal divisor, in the space we can define a dual 1,1 form. This is 4-cycle. In the Calabi-Yau threefold, we could define a dual 1,1 form that could now support via M-theory crutch an additional U1 gauge field. So what I'm saying is the appearance of this, okay, additional section. Maybe I should probably do that now and let it dry. Okay, so let me just, I hope I can write on this one, though it's still wet. Okay, so what I'm saying is appearance of S1, which is a 4-cycle via Poincare duality. We would define 1,1 form that would then, via M theory, as we Kaluza-Klein reduced 3-forum gauge potential, produce gauge field A1. And that would be, in principle, U1 gauge field. And it has nothing to do with codimension 1 singularity. It's really supported by this regular divisor, okay, that comes from relating it to appearance of a section. Okay. The story is a little bit more complicated because, as Timo told you, you know, a lot of U1s that we thought we would have in F theory are not really, they are in M theory but not in F theory. And because we have a vibration, okay, it's not really Poincare dual of that 4 cycle that we have to construct, but we have to construct 4 cycles that are basically complementary to all the vertical divisors and to the 0 divisor. Okay, because only in that way, via FM theory duality, we would get proper U1 gauge field of F theory. Okay, so what we really have to do is we have to define divisors map of this additional section, divisors that are complementary to vertical divisors. Okay, that would be any divisors that we pull back from the base into the ambient Calabi-Yau space. So that would be pullbacks of any divisors in the base that Timo also discussed, and then of course all the resolution divisors. Okay, as well as the class of divisors associated with the 0 section. Okay. It's only once we do this map onto the, so it's not this divisor, but really divisor that is complementary to all those guys. Okay, so that map onto this complementary set of the divisors, that would be the right one to describe by Poincare duality the gauge field, is obtained via what we call Shielda map. I think it's Shielda-Tate map. So what it does is you take a section, an additional section as one, right? And you map it to define a class of divisors. And of course, naturally, you would want divisor that is naturally just coming from the as a homology dual of the sorry, this is as one, this one, homology dual of the original divisor. But we want to make it not to intersect, to be complementary to all those other divisors. So that forces us to define the class of divisors that support via Poincare duality gauge field, U1, to be a combination of the natural divisor of a section as 1 minus divisor of 0 section minus pullback of divisors in the ambient space of the base divisors, and then still in addition we have to make it complementary to resolution divisors that support non-abelian gauge symmetry, and that turns out to be a specific linear combination of this resolution divisor, where these are fractional numbers that we can calculate by intersecting as 0 and as 1 with EI, basically something like that, and some inverse of Cartan matrix. If this is I, then it's J, and now I'm intersecting that, of course, with the curve divisor of this. This is P, J, I, of particular of a particular P1 blob in the resolution of this divisor. Anyway, those are fixed numbers. It's trickier. Okay, so constructing properly map onto the divisors that are complementary to this other vertical divisors plus 0 class divisor requires non-trivial map like this, and that of course complicates the actual constructions, but this can be done. It's well defined. Okay, so it's actually this divisor now that we, via Poincaré duality now construct 1,1 forums in this threefold associated with this divisor classes complementary to all the others. Okay. And then if you do very careful analysis from M theory to F theory, you see that it's precisely this forum that survives in F theory and corresponds to genuinely canonical extra U1 gauge field. Okay. Due to lack of time, I mean, I'm just saying those things in words, but sort of he's giving you a first glimpse of how to basically one can do that. So now let's look at an example. Okay. So what I basically would have to do is I have to have elliptic vibration where in addition to 0 section I would have this rational section and show you how this rational section appears. Okay, so let me see how are things going. How much time do I still have? I started at 2.
25.
Oh yeah, oh it's only 1 hour 15, of course, yeah. Somehow I wanted to give myself an extra 15 minutes, and yeah, I was so mean to all the other speakers. In any case, let's go on, and so this is now the appearance of U1 gauge symmetry, and let me show you an explicit example. Oops. Well, one can systemize construction of additional sections, okay? But I'm just show you one example, actually one of early example. All right. So example. Example. Oh, maybe not yet, okay? Bear with me. I want to show you, yeah, because I emphasize the appearance of matter. I want to argue with you. There is appearance of matter that is localized at Coulomb too. And I can show you that just with Weierstrass parametrization, and then I'll do the example, sorry. So let me just convince you that there is generically a matter associated with this divisor. Okay, so what we have is so the way we see the appearance of matter is starting with, let me just start for concreteness with Weierstrass parametrization, right? Is y squared is x cubed plus f x z to the 4th plus g z to the 6th. And I'm saying is in addition to 0 section, I would have for special values of f and g, I would have to satisfy the condition for the section that would solve this equation in the field of the Bn coordinates. So this is for x. This would be existence of additional section would have to solve this equation. Okay. So and z1. Okay. So as1 section will be parameterized by the values of coordinates x1, y1, z1, okay, that will now solve this equation and will be expressed in terms of some holomorphic birational polynomial of the base coordinate, okay. That would require some specialization of f and g, and let's just assume that we homogeneered it, that we can indeed find a new section that satisfies this equation. Okay. Now if I subtract those two equations, okay, this is general Weierstrass parameterization, this is the condition for existence of rational section. This tells us, if I subtract that y square minus y1 square is x minus x1. Oh, and I'm going to specialize, I'm going to scale out z1 because I won't have it at z0. So I'm going to scale out that. So once I scale that, I subtract that, I get 1 power of x minus x1 from here. Then I have x squared plus x1 x2, x1 x plus x1 squared, and then there is plus f. Okay, so we see that this is the equation now that this vibration has to satisfy in the presence of additional rational section. Okay, and what one sees it is that in codimension 2, so in the base, okay, at codimension 2, there is a point where fiber degenerates. Okay, so the way I'm going to find this codimension 2 point in the base is requiring that f is equal minus 3x1 squared and y1 is equal 0. Right? Those are all equations. x1, y1 are rational points that depend on the base coordinate. So that specifies, two equations specify codimension 2 locus in the base. So this is codimension 2 locus, codimension 2 locus. Okay? So at this codimension 2 locus, okay, the Weierstrass equation, now in this new form, right, because we have additional section, becomes y squared is equal x minus x1 squared x plus 2x1. Okay? So this is now the equation that tells us how fiber behaves above this codimension 2 point. And this is the typical, I think, Timo, did you use that? Did you point out to this conical? Okay. In any case, we see that the fiber now in this case, so at this codimension 2 locus specified by that, the fiber itself actually degenerates. It degenerates precisely at y equals 0 and x equal 1, x1. So according to conditions for singularity that Timo spelled out, okay, this turns out to be singular fiber. Singularity of codimension 2 in the full space, okay, is called conifold singularity. Singularity. Okay. So what we have observed with the existence of additional section, first we argued existence of cycles that support, 4 cycles that support the U1 gauge field, but now we are arguing that existence of section tells us that in codimension 2 we have a degenerate fiber, okay, which corresponds to appearance of matter. So this signifies appearance of matter at this codimension 1 singular. It's hard to visualize that we had this non-singular divisor, and somehow now we generate with the existence of this non-singular divisor, right? That wasn't codimension 1. In codimension 2, on the base, we realize the appearance of codimension 2 singularity that signifies the matter. So what do? This in codimension 2, the theory is singular, so now we resolve. Okay. And what we have now is, in the resolution, we typically get, now this is degenerate, so this is only drawing fiber. Okay, what we get is typically, again, I2 fiber. So there's, you know, we resolve this, this is now resolved, we write y hat, n plus 1, associated with this codimension 2, and the fiber above this codimension 2 locus, okay, now is written as a regular locus of 2 p1s. So this would be p1 plus, p1 minus, okay. Now we have to sort of check what happens to the additional section. Okay? So we could encounter in this resolution two possibilities typically. Okay? One is that, so we have 0 section, say it's here. So this is now in the fiber, this is sorry, not 0, yeah. So let this be now the additional rational point S1, and then of course we also have the S0. So that could be example like that. Okay, and so what we have to now do is intersect this vertical divisor defined by a Shielda map of the additional rational section and intersect it, say, with the, in this case, let me intersect it with P minus 1. Okay? In this case, when I intersect this divisor, right, with this P1, which would specify now the meta curve in this context, this would be, this would have intersection typically 1. I'm a little sketchy with this. Okay? But now, what can happen also is that this additional rational point actually starts wrapping the whole blow up of the P1. So what can happen, this is possibility 1, but there is also possibility 2, where I would have a situation like this. Okay, I would have still 0 section, no, 0 point, but now S1 will start wrapping this whole P1 plus. Well, I'm sorry, bear with me. I think I should have, in my notes, that's the right way of writing it. So this is P minus, and this is P plus. Okay, so now I have this is now it can happen also that in the we have a resolution associated with dimension 1 singularity where this S1 rational point actually dissolves and starts wrapping, in this case, P plus 1. Okay, and this situation now when you intersect the Shielda divisor with P1 minus, this will give you charge 2. Okay, that somehow is associated with those 2 points touching in this I2 fiber, the meta curve with which I'm intersecting the origin divisor. Okay, so what we observe is generically what we get with additional rational section, we get matter at codimension 2 that can generically either have charge 1 or charge 2. Okay, so that's, of course, there could be further specialization that can also potentially give us higher charges. Anyway, this is as far as matter goes. Okay, so now let's go to a concrete example. Okay, so concrete example. By the way, the example that I'm choosing to talk from is actually in the paper. I think didn't I give you some of the, I haven't given you that yet. So this is this one. Okay. N equal to case. This is a later one. There is 1202, but I will have to maybe by the end of the class, maybe I can add this later. In any case, so there is a concrete example, okay, that I can construct that has an additional rational section. So, for example, what I'm going to write it is, I'm going to write the vibration as a hyperplane constraint in a weighted projective space of the type 1, 1, 2, with coordinates. So this is u, v, w. Okay, and it is and the hyperplane constraint that would be consistent with elliptic vibration is would be of that form. W square is some sections Ci of the line bundles of the base, U4 minus I, Vi. I goes from 0 to 3 plus 1/4 B square V to the 4th. So Ci's and B square are some sections of B itself. B itself are some sections of line bundles on the base. Okay, and they would be specified in such a way that this is indeed the elliptic curve. Okay, I can map this elliptic curve to Weierstrass curve, but let me not go into it. It's possible to do it. So I want to point out that this particular choice is something specific that I've done with this quartic equation, right? W square is some quartic in U and V, okay, by specializing coefficients in a special way. So I chose this to be B to be a section of the line bundle, okay? So now we can see that there is that we have actually two sections, S0 and S1. Okay, and they are obtained by okay, let me just make sure that I'm doing that right. Yeah. The way you see the way this thing works, it factorizes. This can be written as u times some cubic, because there's always 1 power of u here, right? Plus this one. So it's a special quartic. And then we see that now I can solve that for rational sections by setting u equals 0 and w square equal 1/4 b square v to the 4th. Okay. Or in other ways, what I have is that w can be plus or minus 1/2 b v to the square. Okay, so the rational section solution is associated with choosing u to be 0 and relating w and v. And you see, this is maybe back to your question. This is a section, so I really have the rational relationship, actually even simpler, right? So I can always scale the coordinates. So the section S0 and S1 are parameterized by taking u equals 0. I can scale v to be 1, and then the rest, w has to be either plus or minus 1/2 b. Okay, and this is perfectly well-defined rational section in that sense. Okay, so this is just maybe to answer your question. That's an example. It can be mapped onto Weierstrass map. Right? And as a consequence, you can further analyze now appearance of matter, because on general grounds, existence of this additional section always produces for me generically codimension to singularities, and they appear in two types of charges typically. Okay, right. So this is an example for really constructed elliptic vibration that has naturally U1 and naturally has matter both with charge 1 and charge 2. Okay. Now I have only 5 minutes to tell you how this could be potentially related now to discrete symmetries. Okay. And what I'm going to do is I'm going to make more general hyperplane constraint of the torus vibration by changing this coefficient, not B to be a section of a certain line bundle, but writing B square to be a section of certain line bundle. So 1/4 b square will be now written as a section. This will be now a section, some polynomial, right? But not be. All right. So this is actually more general thing, where this becomes some square of a polynomial, a certain polynomial of the base coordinates, then B becomes a section. But in general, only C4 is a section. No, is a section of line bundle on Bn, or in this case B2. Okay. Now, if we look for the solutions for points for non-rational sections, the rational section condition was related to B being a section. Okay. Now, when I replace B squared with C, those are not sections anymore. In this case, this vibration lost both sections. Okay? Because, you know, the equation for what I would like to call the sections, right, with now B being the section of a line bundle, now I get a condition that U is 0 and W is plus minus square root of B, square root of C4 B square. This is not a section, because this is not anymore a polynomial, right, the basic. So this is no sections anymore, but only bisection. Basically what I'm saying, if I go to covering space and square all those coordinates in some covering space, then W square would be related to W to the 4th by a section type condition. Okay, and geometrically we see this happening really as deformation that I had before with sections, and now changing it into new geometry that doesn't have any section. So I'll try to wrap it up in just a minute or two. So going to Z2, in this case, what we have seen now in geometry, we started with some vibration that had two sections, and let me just, so this geometry at some dimension 1 degenerates, and then before we had both S0 and S1, right, and then the sections. So let me just forget about the base, because we know what happens. So if we go in vibration, we have now the sections that then at some point collapse, and then, keep on going in vibration, and then there is regular vibration again. So this section then keep on behaving. This is now back S1, and let's say this is S0. So this would be now this geometry with two sections with S1 and S0. Okay? And then at some point in codimension 2, it degenerated, and we knew matter appeared there. Right? And in particular, we got example where matter with charge 2 appeared, with Q equal 2 appeared. That was when, there's one of the resolved P1, the extra rational point wrapped the extra P1, okay? All right? But now the other geometry is different. When I replace before B square with just a line bundle, section of line bundle C4, what has happened is we started, we have basically gone to now new deformation. It was complex structure deformation because we changed B square into just C4. And now what happened is this codimension 1 singularity was actually now resolved by gluing in some 3 sphere, and what we got is now the regular space here and these collapsed sections were actually now glued. They were glued here into, so S1 was here and S0 was here, but now with this deformation, when we turn on C4, at this codimension 2, there was no singularity anymore, but the sections were glued. And so globally, we don't have separate sections S1 and S0, but those are now bisections. Okay? Now I want to argue that this geometry supports discrete symmetry. This was geometry, but I'm not going to argue now with field theory. Okay? And the way I'm going to argue with field theory is when I went from this space that had this codimension 2 singularity by turning some complex structure deformation and changing this B square into C4, right? I have basically done some complex structure deformation and got into this space where sections disappeared and they were sort of glued now into bisections. Okay? But in field theory, what has happened is at this location we have massless matter in this theory with U1. We have theory with U1 and we have massless matter with charge 2. This deformation of a space here, right, this complex structure deformation that get us to bisection is in field theory interpreted as getting vacuum expectation value to this field that appears here. It turns vacuum expectation value the U1 because this guy has charge 2. It breaks U1, but it doesn't break it to nothing because of its charge being 2 is broken down to effective theory with the Z2. Okay? So this is how in field theory and knowing how to identify matter, and now with higher charge we go into a new geometry, but via field theory we see that we are now in the F theory, okay, with gate symmetry being just Z2. Okay. Doing direct calculations in these geometries with bisection is tough, but we can use this crutch of this geometry that we know so well with additional section, okay, and matter, and doing field theory to realize the appearance of F theory now, describing the theory that has only discrete symmetry, but still gauge discrete symmetry. There are some other beautiful things of relating the geometry of these bisections and also map of this bisection geometry to Weierstrass map to elements of Tejchafarevich group that are related to M theory vacua. F theory doesn't care whether you write it on a geometry with bisection or its map onto Weierstrass map. Okay, both of them would describe or as the same F theory, but M theory cares. It's another beautiful story that I could have told you, but I don't have time. So Tejchafarevich, which is associated with Weierstrass map of this geometry, and this Y, which is bisection. So this is our Yn. And this was the original Y3 with extra section and U1. So this different geometry, Weierstrass map of this geometry, and this bisection geometry are elements of Tejchafarevich group, and they are related to different M theory vacua. As Timo told you, once we go, even if we don't have any gate symmetry in F theory, in M theory we always have Kaluza-Klein, right? U1. In this case corresponds to some linear combination of this U1 in 6 dimension, Kaluza-Klein U1. So this is KK plus the one in F theory, so 6D. This one here, and that is a surviving one here in M theory. But this one is actually U1 KK cross Z2. All right, so they are different M theory vacua associated with different geometries. Geometry with bisection gives us a theory with an extra U1 combination of this U1 and the KK, but this one sees that. So anyway, and there are complications and beautiful things that one can say when n is bigger than 2, and I supplied notes for that. You can at least oversee that and get the references. And also further stories both in particle physics constructions, like example of the three-family standard model, supersymmetric standard model that I also highlighted. But we'd love to include and construct standard models also with R parity as his gun that Lian Tao talked to you about, that would be realized via this gate Z2 symmetry. Still have technical problems, but implementing all these techniques at the end to apply it to construct particle physics models. Okay. Now, I hope you got some glimpse of how far we can get with studying F-theory, both from Timo's lectures and sort of some things that I tried to highlight for abelian and discrete symmetries for you. I think we made tremendous advances. I think we tied these ideas to deep mathematical techniques, both in algebraic differential geometry and now also in number theory. Okay? And we got some particle physics, but we are not there. We are really not there, because what I told you mainly about is discrete data, right? Non-abelian gate symmetry, number of matter, charges of matter. Timo told you about Yukawa couplings, right? But how about numbers? Size of Yukawa couplings, okay? Further properties of the effective theory, right? Not just discrete data that we got from these beautiful techniques in mathematics, right? So there is more to do, okay? And maybe in a few years we'll have another TASI school and one will report on that. Thank you.
Along the elliptically fibered Calabi fold, finding multiple sections is something common or something rare?
Well, it often happens. You see, the approach that we took and that I took here is mainly from the fiber. I told you almost nothing about the base. I just said, you know, if I construct vibration that I have these sections of some land bundles that are of this form, right? I can identify already in the vibration where I have U1s, right? But then there is also approach, if the base is specific, then that also feeds back in some cases because it could specialize further vibrations. And I think people like Watty or Morrison, they try to do that more from the base up. Approach that Timo or our group took was more from the fiber side because it's more general.
In the generic model, I have multiple U1s.
Yes, but you know, in the generic fibril construction like this, we really were able to get those things down only to 3 U1s. But with concrete base, you can see how many extra sections you have. So there's some progress that could be made from both sides, from the base and from the fiber. Okay, but I hope I gave you a little glimpse of some of these ideas. Okay. Any other questions? Okay. Oh yes. Yeah.
Gauging the T2 gauge group to reduce your number of complex particles.
Sorry, could you say it again?
So if you have a T2 gauge group rather than not on a certain base.
Oh, Z2. Yes.
It changes your number of complex structure constants.
Complex. I think. I have to check that, But I have done deformation in complex structure model. I have deformed the space in a way, right, that actually look more general to begin with, right? But the full-fledged counting, Okay. Yes.
So I want to ask whether a model have proportion.
Again, I didn't mention that. I did only the free part, right? And it's a billion group, and the addition associated with the addition of those sections, right? Of elliptic vibrations. There could be a torsional part, and there would be another lesson that I'm sure, if we had time, Timo could have said he worked on that extensively. The net effect is that appearance of torsion of Mordell-Weil group typically changes the global structure of non-abelian gauge symmetry. So namely, typically you have to mod out by the torsional part of the Mordell-Weil group the resulting non-abelian gauge symmetry. So that's the net effect. But they are, Okay, thank you. So maybe I would, thank you, but I would want to really thank local organizers, especially Tom and Emily and Oliver and Shanta for the tremendous effort that they put into making this the school running so well for all of you. So I think they really deserve a special applause and thanks. And you too.
I want to thank Andre Shelton for doing the AV for us, Veronica Lingo for doing the web page and the photography. So let's go around for applause for them.
Yeah.
And also, so Mirjam, Cvetic, and Georg Kudnoff were the scientific organizers. All of the speakers they invited, they organized the sessions, all of the wonderful talks. And also my talk that you got to hear are all because of them. So I think this was a fantastic program, and I'm really grateful to Igor and Mirjam for everything that they did. So thank you very much.
Thank you. Okay. So on this note, I think the school is over. Yeah.
All of you, it's a really wonderful school. Thank you.
Yeah.
A couple of questions.
Yes,
Can
yes,
you mention
yes.
again last thing you said about the torsional factor?
Oh yeah, the torsional part, what it does is basically you can identify and you construct locally, right?
Yeah, that would be Emily, but I don't think Emily's here right now. In terms of like having like a professional.
Okay.
I'm sure that you could just gather everyone.
What this does is
And make it now. I can turn on the mic right now if you want to ask people.
Okay, let me. Can you turn on the mic?
Yeah. That should still be on.
Hi, guys. I just wanted to make one quick announcement that maybe we can take like one last photo with shirts outside, maybe the same spot we were before, because I guess here it's difficult to organize. So, I mean, just to post it on Facebook and stuff. So, whoever wants to join is welcome to join. All the lecturers are welcome to join if they care to. So, yeah.